Summer heat is not a modern problem. It is one of the oldest threats humanity has ever faced. Long before thermostats, refrigerators, or air conditioning, ancient civilizations were battling temperatures that killed crops, collapsed armies, and emptied cities. Yet they survived, and in many cases thrived. The ancient Egyptians, Romans, and Chinese did not fight heat with machines. They fought it with architecture, behavior, biology, and culture. Their solutions were not primitive guesswork. They were the product of centuries of careful observation. And many of those solutions we are only now rediscovering. This is the story of how three great civilizations beat the heat, and what we can learn from them today. Part 1. Ancient Egypt, built to breathe. Egypt sits at the edge of one of the most punishing environments on Earth. Summer temperatures in the Nile Valley regularly exceeded 40 degrees Celsius. The desert offered no mercy. Yet the Egyptians built a civilization that lasted over 3,000 years. Heat was not an obstacle, it was a design problem, and they solved it brilliantly. Architecture as air conditioning. Egyptian homes were not built for aesthetics, they were built for airflow. Walls were thick, often half a meter or more, constructed from mud brick, a material with exceptional thermal mass. During the day, those walls absorbed heat rather than transmitting it inside. At night, when temperatures dropped, the walls released that stored heat slowly, keeping interiors stable. The result was a natural buffer against the sun's peak intensity. Windows were small and positioned deliberately high on north-facing walls to catch the cooler prevailing winds while blocking direct sunlight. Some wealthy households installed wind catchers, vertical shafts that funneled breezes down into lower rooms. This principle, known today as passive ventilation, is still used in sustainable architecture across the Middle East. Water as a cooling tool. Egypt's relationship with the Nile was not only agricultural. Water was integrated into daily life as a thermal regulator. Courtyards featured shallow pools that cooled the surrounding air through evaporation. Wet reed mats hung across doorways created a rudimentary form of evaporative cooling, the same physics used in modern swamp coolers. The elite slept on raised beds to avoid floor-level heat accumulation. They used fans made from ostrich feathers and palm leaves, not merely for luxury, but as a functional cooling technology. Servants fanning noble families in tomb paintings were performing a real physiological service, accelerating evaporation from the skin. Clothing and diet. Linen was Egypt's fabric of choice, and this was not accidental. Linen is one of the most breathable natural fibers available. It wicks moisture, dries quickly, and allows air circulation against the skin. White and pale colors were dominant, reflecting solar radiation rather than absorbing it. Diet adapted seasonally as well. Fruits with high water content, figs, melons, pomegranates, dominated the summer menu. Fermented drinks like beer provided hydration with caloric value. Heavy meat-based meals were reduced in frequency during peak heat, an intuitive recognition that digestion itself generates metabolic heat. The siesta culture. Perhaps most significantly, Egyptians restructured time itself around heat. Work began at dawn, paused during the hottest hours of midday, and resumed in the late afternoon. This behavioral rhythm, what we now call the siesta pattern, was not laziness. It was thermodynamic rationality. The body's most demanding labor was performed when ambient temperatures were lowest. Part 2. Ancient Rome, the engineering of cool. Rome was an empire of engineers, and they brought that engineering mindset directly to the problem of heat. The Roman summer, particularly in North Africa, the Middle East and the Italian peninsula, was brutal. Yet Roman civilization built some of the most thermally sophisticated environments the ancient world had ever seen. The Thermae, engineering comfort at scale. The Roman public bath, the Thermae, is often described as a social institution. That is true, but it was also a precision thermal management system. The baths offered a sequence of rooms ranging from cold, frigidarium, to tepid, tepidarium, to hot, caldarium. Romans moved through this sequence deliberately, using temperature contrast to regulate core body temperature. Entering a cold pool after heat exposure triggers vasoconstriction, reducing peripheral blood flow and rapidly lowering skin temperature. This is the same mechanism used in modern cold plunge therapy. The Romans did not know the physiology, but they understood the effect, and they institutionalized it across hundreds of bath complexes throughout the empire. Hypercaust and passive cooling. The hypercaust, Rome's underfloor heating system, is well known. Less discussed is how Roman architects inverted the same principles for cooling. In hot provinces, buildings were oriented to minimize direct sun exposure on south-facing walls. Porticos and colonnaded walkways cast constant shade across streets and public spaces, turning entire city blocks into thermally moderated corridors. The atrium, Rome's central courtyard feature, functioned as a thermal chimney. Hot air rose and escaped through the open roof, the compluvium, while cooler air was drawn in from surrounding rooms. A shallow pool, the impluvium, at the center, captured rainwater and provided evaporative cooling. Elegant, passive, and remarkably effective. Fabric, food, and ice. Roman elite had access to a luxury that defies expectation. Ice. Snow was packed in insulated pits in the mountains and transported to cities, a cold chain that predates modern refrigeration by 2 millennia. Emperor Nero was reported to have chilled his wine with alpine snow. This was not purely indulgence. It was a demonstration that Romans understood cooling as something worth engineering at significant logistical cost. The toga, Rome's formal garment, was heavy, unsuitable for summer. In practice, Romans in hot provinces wore light tunics of linen or lightweight wool. Pragmatism overrode formality when survival was at stake. Meals during summer leaned toward cold foods, fresh vegetables, and lighter fare. Garum, fermented fish sauce, provided salt replenishment, critical for replacing electrolytes lost through perspiration. This was not nutritional science, it was cultural knowledge accumulated over centuries. Urban planning as heat mitigation. Roman city planners placed trees deliberately along streets and in forums. Aqueducts did more than supply drinking water. They fed fountains throughout cities, creating microzones of evaporative cooling in public spaces. The density of Rome's urban fabric, often criticized, also meant buildings shaded each other, reducing the urban heat island effect that plagues modern cities. Part 3. Ancient China. Harmony with the season. Chinese civilization developed its approach to summer heat within a philosophical framework as much as a practical one. The concept of yin and yang, the balance of cool and warm, passive and active, shaped how Chinese society thought about heat, not as an enemy to defeat, but as a force to navigate. Architecture of the courtyard. The traditional Chinese courtyard house, the Siheyuan, was designed around a central open space that functioned as a thermal regulator. During summer days, the courtyard acted as a heat sink, drawing hot air upward and away from surrounding rooms. Trees, particularly Polonia and scholar trees, were planted specifically to shade the courtyard during summer, while shedding leaves in winter to allow sunlight through. Roofs were designed with pronounced overhangs that blocked the high summer sun while allowing the lower winter sun to penetrate. This geometry was not decorative. It was solar calculation encoded in carpentry. The precise angle of roof overhangs varied by latitude. Southern Chinese architecture differed from northern because the solar geometry differed. Interior walls were often finished with materials that absorbed and released heat slowly. Floors used stone or tile, materials that remained cool underfoot even when air temperatures rose. Furniture was elevated. Beds were fitted with cooling mats made from bamboo or rattan that allowed airflow beneath the body. In summer, households physically restructured their sleeping arrangements, moving to cooler northern rooms and lower floors. Traditional Chinese medicine and thermal intelligence. Chinese traditional medicine offered a systematic framework for surviving summer. The concept of shanghan, harm from cold, had its summer counterpart in zhongshu, heat stroke or summer heat injury. Physicians categorized foods, herbs, and behaviors by their thermal properties. Foods classified as cooling, mung beans, lotus seeds, bitter melon, chrysanthemum tea, were prescribed for summer consumption. These were not random superstitions. Many cooling foods are high in water content, rich in electrolytes, or have demonstrated anti-inflammatory properties. Mung bean soup remains one of the most consumed summer foods in China today, its biochemical properties now partially validated by modern nutrition science. Green tea consumption peaked in summer, not only for its hydrating properties, but for the catechins it contains, which have vasodilatory effects that can marginally reduce perceived heat stress. Chinese physicians understood this through empirical observation long before biochemistry existed. Behavioral and social adaptation. The Chinese summer calendar was punctuated by specific cultural events tied to heat management. The Sanfu period, the 3 hottest stretches of the Chinese summer, was formally recognized in the almanac, and behavioral guidelines were issued for each phase. Reduced physical exertion, adjusted diet, increased sleep, and avoidance of emotional agitation, thought to generate internal heat, were all prescribed practices. Silk was the premium cooling fabric, lighter than linen in thin weaves, with a natural temperature-regulating property due to its protein fiber structure. For those who could not afford silk, loosely woven hemp provided similar breathability. Color choices were light, white, pale blue, sage green, for the same radiative reasons as in Egypt. Fans, shan, were a technological and cultural artifact simultaneously. Folding fans, invented in China during the Song dynasty, were engineering achievements, portable, lightweight, and capable of generating localized airflow efficiently. The fan was also a social object, its design communicating status and refinement. Function and culture reinforced each other. Part 4. Common threads and modern lessons. 3 civilizations, 3 continents, 3 distinct cultures. And yet the patterns converge with striking regularity. The convergence is not coincidence. It is evidence that these solutions were discovered independently because they were responding to the same physical reality. Thermal mass works. All 3 civilizations built with materials that absorb heat slowly and release it slowly. Mud brick, stone, rammed earth. Modern architecture has largely abandoned thermal mass in favor of glass and steel, creating buildings that heat rapidly and require enormous energy inputs to cool. The lesson? Building materials are not neutral. They are thermal partners. Passive airflow is powerful. Courtyards, wind catchers, porticos, and compluvium openings all exploit the same physics. Warm air rises, cool air fills the void, and strategic openings channel airflow without any mechanical input. Modern passive house design and bioclimatic architecture are rediscovering these principles, but they remain underutilized in mass construction. Behavior must adapt to climate. All three civilizations adjusted when they worked, what they ate, and how they moved in response to seasonal heat. Modern society has largely decoupled behavior from climate. We work at the same hours year-round, eat the same foods in all seasons, and rely entirely on mechanical systems to compensate. This is both energetically expensive and physiologically suboptimal. The ancient model, shifting schedule, adjusting diet, reducing exertion at peak heat, remains biologically valid. Cooling foods are real. The dietary adaptations of Egypt, Rome, and China all converge on high water content foods, electrolyte replenishment, and reduced heavy protein consumption in summer. Modern nutritional science confirms the logic. Hydration, sodium balance, and metabolic load management are genuine factors in heat tolerance. These were not myths. They were empirical findings dressed in the language of their time. Community cooling matters. Rome's thermae, Egypt's communal wells, China's shared courtyard spaces, all provided access to cooling that was not dependent on individual wealth. The cooling infrastructure was collective. This model has modern relevance as climate change intensifies urban heat islands and heat-related mortality rises disproportionately in low-income communities. Public cooling spaces, libraries, pools, shaded plazas are not amenities. They are infrastructure. We live in an era of accelerating heat. Summers are longer, more intense, and more dangerous than at any point in recorded human history. Our primary response has been mechanical: more air conditioning, more energy consumption, more carbon emission, which in turn drives more heat. It is a cycle the ancient world never created. The engineers of ancient Egypt, Rome, and China did not have access to our technology. But they had something arguably more valuable. They had no choice but to solve the problem correctly the first time. Every architectural decision, every dietary practice, every behavioral norm was pressure tested over generations. What survived was what worked. We do not need to abandon modernity to learn from antiquity. But we would be wise to listen more carefully to what 3,000 years of human experience has already figured out. The answers were never lost. We simply stopped asking the questions.